Hi there, and welcome to the lecture on atomic theory. This will be our first lecture for Atoms 1 of Unit 3. Our key ideas for this section: who came up with the first theory of atoms? What did Dalton add to the atomic theory? How did Thompson discover the electron? What is Rutherfords atomic model? And what is the modern model of the atom? So the first question we're going to start looking at. So in the 4th century BCE, so before the Common Era, the Greek philosopher Democritus suggested that the universe was made of invisible units called atoms. So he was technically the first one to describe the term atom. However, Democritus was not able to collect any evidence for this atomic theory. So at this point it probably wasn't considered a theory, more of a hypothesis or an idea. So then we move on to Dalton's atomic theory. And according to Dalton, all atoms of a given element were exactly alike, and atoms of different elements could join to form compounds. And Dalton was the first to use experimental evidence to support his theory that there was something going on. He came up with the law of definite proportions. This says a chemical compound always contains the same elements in exactly the same proportions by weight or by mass. So we could say, if we think about water, the element or the compound water, if we write out the formula for it, H2O, it has a definite proportion. We always have 2 hydrogens to 1 oxygen in order for it to be water. If we were to add a hydrogen, we don't have water here anymore. What we have is actually a hydronium ion, because we've got a positively charged water molecule, so we've got an extra hydrogen there. Not something that's important for you guys to know, just the proportion part. So in order for a compound to be what it is, you have to have the same, it has to have the same number of each element. So if we were to figure out the composition by mass, we can see that oxygen or water is 89% oxygen, 11% hydrogen. So this doesn't really lead to the H2O part, because we have twice as many hydrogens as we have oxygen, but there's more mass in an oxygen molecule, and we've got some different ways to show this, the pie graph, or visually we can show that the hydrogen is a lot smaller than the oxygen atom. However, it was found that this theory did not fit all observations. So we move on to Thompson, and Thompson is credited for discovering the electron. So Thompson did an experiment with a cathode ray tube, similar to what we find in those big tube TVs. His experiment suggested that cathode rays were made of negatively charged particles that came from inside the atom. And here we've got a visual of a cathode ray tube. So what he would do is put an electrical source, hook this up to a vacuum, so he took out the air. This is basically like a light bulb. There's no air inside of a light bulb either. And we could view the electrical signal being transferred through this tube. So it kind of looked like a light bulb. It's a green ray of particles. And when we brought a magnetic source close to this, we would see that this ray, this beam of light, would bend away from or bend towards, depending on whether the magnetic source was positive or negative. So the positive source positive source would push this ray away. I'm sorry, push it or pull it towards, and a negative source would push it away. Thompson also developed what we call a Plum pudding model based on his cathode ray tube experiment. He did discover an electron, and we define electrons here. It is a subatomic particle that has a negative charge. And what Thompson's Plum pudding model said is electrons are spread throughout the atom. So we kind of draw like a muffin, and then how blueberries are spread throughout a muffin. So let's see if we can draw a picture here. So if we say this is a muffin, we've got our blueberries that are kind of spread throughout. So Thompson was right about the electrons. His model of the atom, not so much. So we move on to Rutherfords model of the atom. Rutherford proposed that most of the mass of an atom was concentrated at the center of the atom. And he did an experiment that we call the gold foil experiment. And this gold foil experiment allowed Rutherford to discover the nucleus. And we define a nucleus as the atom's central region, which is made up of protons and neutrons. So this kind of signifies the Rutherford model of the atom. We said that the nucleus is this positively charged center that's found within, and then the electrons are outside the nucleus. And he also said that it was mostly empty space that the atom was. So what he did with this gold foil is he had this gold foil, and what he did is similar to launching maybe marbles at a screen, but he shot something called an alpha particle at this gold foil. And what he found, most of the time, these particles would shoot right through this gold foil and hit the back of this ring. So this ring was like a way for him to collect these alpha particles. But every once in a while, they would bounce off and hit like over here, over here. What this was showing is these positively charged alpha particles are coming in contact with this positively charged nucleus and bouncing back towards this beam of light. So when most of these particles are going through the gold foil, that's telling the experimenter, Rutherford, that we've got a lot of empty space. But then when it hits the nucleus and bounces back, that tells us that there's positive charge in the middle. So our modern model of the atom, and the modern model of the atomic model, electrons can be found only in certain energy levels, and they're not going to be found between levels. Furthermore, the location of electrons cannot be predicted precisely. So we have an idea of where we can find electrons, but we're not going to be able to find an electron. Electron location is limited to energy levels. So an atom has so many energy levels, and depending on how many electrons that atom has will depend on how many electrons and energy levels it has. So in Bohr's model, electrons can be in only certain energy levels. They gain energy to move to higher energy levels or lose energy to move to lower energy levels. So when these electrons become excited and they gain energy, they move out to higher energy levels. So we view electrons now like wave particles, so they act like waves. The exact location of electron cannot be determined, we said that already. And now we view the electron model as far as orbitals. So we say the electrons are found in orbitals, and this orbital is a region in an atom where there's a high probability of finding electrons. It's not exactly where we can find them, but we'd say that 90% of the time we should expect to find the electrons within this space we call the orbital. And these orbitals take different shapes depending on how many electrons there are in an atom. The first two are spherical shapes, so kind of like basketball shaped around the nucleus. Then they kind of take different shapes after that.
Thompson discovered the electron and proposed the Plum pudding model, where electrons are spread on the surface of a solid, positively charged sphere. The discovery of the electron showed that the atom is, in fact, divisible. Rutherford learned that atoms are mostly empty space with negative electrons scattered around a positive center. This model describes a central part in the atom, the nucleus. Bohr's model suggested that electrons move in orbits around the nucleus. Bohr was the first person to be able to explain why atoms could only give off or absorb energy in specific amounts.
So Bohr also said that the electrons were orbiting around the nucleus, so he kind of had the model that was similar to the solar system, but that's not necessarily true.
We now know that electrons are not solid particles that can orbit the nucleus like tiny planets around a sun. In the present model, electrons are found in regions of probability that are often shown as clouds that surround the nucleus at successively higher energy levels.
So, thanks for listening.